Alright, in this chapter we're going to look at transducers and exactly what they are, partially how they're made, not too much, and discover what some things we need to know about them. Alright, so what are transducers? A transducer is any device which converts one form of energy to another. A light bulb is a transducer. Muscle is a transducer, converting chemical energy into motion. Car engine is certainly a transducer as it converts gasoline into movement. So these are just changing the form of energy. These are all transducers. An ultrasound transducer that we use has two functions. It both transmits energy. It converts electrical energy into sound and transmits pulses into the body. And then it's also more like a microphone where it receives echoes back from the body and converts those sound pulses into electricity. So ultrasound transducer is what we call a bidirectional transducer. It can convert energy to one form and then back again into another form. So that's a bidirectional transducer. It does this by use of the piezoelectric effect. And the piezoelectric effect is there's certain materials that if you change their shape you get mechanical, if you change their shape or mechanically deform them, they will produce a voltage. There's some very natural ones that do this. Quartz is one example. And one of the first uses of piezoelectric materials was that if you put a piece of quartz into the nose of a bomb, it can produce electricity. So when bombs were dropped in World War II, they didn't explode due to the impact with the ground. They exploded because a piece of quartz impacted with the ground and created an electrical charge, which then set off the explosives. So that's how the bombs worked back then. So we have quartz and tourmaline would be two of the natural type materials that are piezoelectric. If you deform them, they create electricity. So there's also a reverse of that, where if you apply a voltage to a material, it will then change shape. And this is known as the inverse piezoelectric effect, or as Dr. Edelman, your author of your book, calls it, the reverse piezoelectric effect. And this is how transducers work, is we apply a voltage to the crystal of the transducer and it changes shape, and as it changes shape it moves air in front of it or moves tissue in front of it, causing a sound wave to be created. So there's lots of materials that can be used as piezoelectrics. The most common that we will discuss is known as the lead zirconate titanate, okay, or also PZT. The elements zirconium, titanium, and lead have the initials Z for zirconium titanate, T, and lead is the element lead is given by the initials PB, so we use the P in that, and so we call this PZT. And I'll be referring to PZT as we go from here on out. And when I say that, just remember that's the crystal that makes up the piezoelectric crystal of the transducer. Now, modern transducers use polymers that are piezoelectric materials. And there's also a piezoelectric material known as MUTS, which stands for the silicon micro machining ultrasound technology, or MUTS. So the one you need to remember is PZT. Just remember that in addition to PZT, other crystals are made of polymers and more advanced materials. So the simplest transducer we can have is one that simply has the piezoelectric material near one end, and behind it is some damping material to stop the vibration of the piezoelectric, and in front of it is what we call a matching layer that makes up the front of the transducer. Behind the damping material is a case that holds it, and then you have a strain relief which keeps the wires from pulling on each other too hard, and of course a cable which connects the transducer to the machine that you're going to be using. So when we look at this transducer, we see the end-on view, and then we see a side view of the transducer where there's many small elements across the face of the transducer, and we'll talk about how those work in the future. And then you have this matching layer, damping material, case, strain relief, and cord. We will talk about why there are so many different crystals in the transducer in just a little bit here. So we have our piezoelectric material, again damping material, the case, strain relief, and cable, and then in the front is the matching layer. These are the transducer components you need to know of. This is what they do. The case protects the internal elements. Its very important job is to insulate the patient and the sonographer from electrical shock. We are going to be using electricity to stimulate the elements, and we don't want that to stimulate us either. There is an electrical shield within the transducer. This is what's known as an electrical ground, and it protects the patient and sonographer, and it helps reduce some of the electrical interference that can occur in a hospital setting. There is an acoustic insulator that provides a barrier between the case and the piezoelectric materials. These piezoelectrics are very sensitive to sound, as you can imagine, and so we have to have an acoustic insulator to keep outside sounds from causing the material to vibrate. There is the PZT, or element itself, the crystal, which is the piezoelectric material itself, the actual crystal that's going to be causing the electrical signals back to the machine or the sound to go into the body. The crystal is a specific size. It is called a 1/2 wavelength thickness of the crystal. And when they talk about the wavelength of this 1/2 wavelength, this wavelength is the wavelength of the sound in the crystal itself. So you can imagine a crystal being a hard rock. It's going to be much faster propagation speed than the human body. So that's where the half thickness comes from, is the measurement of the crystal of the piezoelectric material itself. The wires are simply electrical connections between the system and the crystal, and then we have the matching layer in the front. And as we said, the matching layer is a quarter, well, we didn't say, but I'm going to tell you. The matching layer is a 1/4 wavelength thick. It is, and this assists in getting the sound into the patient. We'll describe why that is in just a moment here. And then we have the backing material, which reduces the ringing of the piezoelectric crystal, which improves what we call bandwidth, and we'll talk more about bandwidth in just a few minutes here. So let's talk about this matching layer. This is important because if we think back to our discussion of the interaction of sound and media in the Chapter 6, we found that at a interface where there's a difference of impedance, you get a large reflection, or you get a reflection back depending on the difference of impedances. Well, the impedance of an ultrasound piezoelectric crystal is significantly different from the impedance of a human body. So if we didn't have a matching layer to overcome this difference, we wouldn't get any sound or very little sound into the body. If you want to use that equation of impedances, remember that the reflection equals the square of the difference of the sum of the impedances, the difference of the impedances over the sum of the impedances. And the human body impedance is about 2 megarails, and the crystal's about 39 megarails. So you can work out the amount of reflection just going from the transducer into the body by utilizing that equation. And I urge you to do so as a good practice to see how little would get into the body. Now, so how do we overcome this energy difference of these impedances? So without a matching layer, it's very difficult for us to overcome these energy barriers. Imagine, if you will, trying to jump 8 feet high. Okay, one person has done this in the history of humans that we know of. This is Javier Sotomayor of Cuba. He jumped 8 foot and 1/4 inch in 1988. That was the only time he ever jumped that high, and nobody else has ever jumped that high since then. Okay, he still holds the world record. Now, the matching layer, if you think about that huge impedance difference between the body and the human, the matching layer is going to help us overcome that 8-foot barrier. And I'll go into how that works. So the impedance of the piezoelectric material, the PZT, is about 20 times that of the human skin. So most would be reflected back, and very little would be transmitted into the tissues for imaging purposes. And then once it went into the tissues and the echoes came back, most of those echoes would be reflected back into the tissues, and we'd get very little back to the transducer at that point. So we have a matching layer, and it's always going to have an impedance somewhere between the PZT crystal and the skin. So very important, all matching layers have an impedance somewhere between the two materials that you're going to have it go between. The gel also forms a bit of a matching layer, maybe not so much as the actual matching layer, but it is also a matching layer too. So that's another purpose of the gel. So when we look at the impedance differences, we see that the PZT has the greatest impedance, the matching layer is next, then the gel, and then the skin. And it's very important that we have this matching layer be exactly 1/4 wavelength thickness, and that's for geometrical purposes, and we're not going to worry about why that is. We're going to memorize that the matching layer is 1/4 wavelength thick. Okay, just as the PZT crystal is a 1/2 wavelength thick. These are just numbers you're going to have to remember. There's no I can tell you the reason for it. It's for geometrical considerations, and I don't think anyone really wants me to go into exactly what those geometrical considerations are, but certainly if you want me to, I'll do it. You can drop in on the next office hours, and I'll be happy to go over that with you. So how can you, as a typical ultrasound student, clear an energy boundary of getting 8 foot high? Well, it's very simple. We use matching layers every day to do this, and you can think of a matching layer as a multitude of steps getting you easily up to 20 feet or higher. So we use matching layers all the time. We call them stair steps. that is exactly what the matching layer is for the transducer. It's a series of steps, and matching layers are typically 4 to 8 layers thick, each one a little different material, so that you get closer and closer to the impedance of the body as the sound starts traveling through the transducer. All right, let's talk about the backing layer. Without a backing layer, we would have very long pulses. The PZT crystal would just continue to ring when we hit it with a voltage. So the backing layer produces a short pulse, and this is very important for axial resolution and imaging. So some of our properties of the backing material is it is a very high acoustic absorber, so it just absorbs the sound. It has an acoustic impedance very similar to PZT, so that the sound doesn't reflect back into the crystal. Okay, the sound easily crosses into the backing layer, and there it's absorbed. Okay, so the consequences of utilizing a backing material give us decreased sensitivity to sound, because it's going to be absorbing some of our sound. It's going to give us something called a wide bandwidth, which is very important, and it gives us something called a low quality factor. Okay, and I'll go over what those two terms are here in a minute. The most important thing to remember to begin with is that PZT material stops the ringing, the backing material stops the ringing of the PZT crystal. Okay, that's the most important thing to remember. Now, let's talk about bandwidth. When we pick up a transducer and we're going to image something, typically an abdomen, you're going to image it around what we say is 4 megahertz. Okay, go to any of the machines in the lab, pick up an abdominal transducer, and it'll probably say something like 4 on it. That means that is the center frequency of the transducer. So the center frequency of the transducer is where the transducer is the most sensitive to that frequency. Okay, so that is the frequency where the transducer is most sensitive to sound touching it. If it touches it at that frequency, it makes the strongest electrical signal back to the system. Now, a bandwidth is the actual range of frequencies, so not just the center frequency, but the entire range of frequencies over which the crystal operates. So if our crystal operates over a multitude of frequencies, and they all do, the center frequency is just the center one, and then the bandwidth is the area which we allow it to operate from the lowest frequency to the highest frequency. So in this case, we're saying the bandwidth is the frequency 2 minus frequency 1. That's going to equal our bandwidth. These are just simply higher to lower frequencies. With imaging probes, we want this bandwidth to be as wide as possible, as great as we can possibly get it. Okay? We've talked about how attenuation occurs and that low frequencies penetrate deeper than high frequencies, and we've talked about how high frequencies are better for axial resolution. So we want both the high frequencies for axial resolution and the low frequencies for penetration in order to do imaging. So wide bandwidth probes are good for imaging, and we call those broadband ultrasound probes. Okay, so let's go back over it. The frequency of the probe is the center frequency. It is where the probe is most sensitive to sound vibrations. It has a kind of arbitrary cutoff that we're going to say is the high-end frequency, and it has a low-end frequency, and those are, the difference between those is the bandwidth. So how do we decide how high our high-end frequency is if our center frequency is f sub 0? Well, the high end is going to be where the probe is is less sensitive by an amount of 3 decibels, or if you remember how decibels work, it's half as sensitive to this frequency at f2 as it was to the frequency at f1. So we have a 3 decibel loss, and we're going to say that's where our high-end frequency is. So when we lose our sensitivity to 3 decibels, we're going to say, oh, that's our high end. When we lose our sensitivity to 3 decibels for the low end, we're going to say that's our low end. Okay, this is called the shoulder of the frequency. Okay, these are the shoulders, and typically they are a 3 decibel drop in sensitivity. Can they be other numbers? Yes, they can be 6 decibels. So that's just something you'd have to look at what the manufacturer has determined the bandwidth is set for. All right, let's move on. What is the quality factor? So a quality factor, and I honestly believe this is a number made up by manufacturers. But it is a unitless number because we're going to take our center frequency and divide it by our bandwidth to get the quality factor. And so center frequency is in megahertz, bandwidth is in megahertz. The units will cancel, so we'll have a unitless number as the quality factor. This is inversely related to the bandwidth. So as the bandwidth increases, the quality factor goes down. Okay, that's why I think this was made up by manufacturers, because that doesn't make sense to do it that way, but that's the way it is. Imaging probes are what we would call a low Q probe, okay, low quality factor probe, and that's because they have a wide bandwidth. This number down here is big, so this number becomes low. There's something called the fractional bandwidth also, okay, and the fractional bandwidth actually is just simply the reciprocal of the quality factor. You can also think of it as the bandwidth divided by the center frequency. So this is another measure of the ultrasound probe. If this is a high number, the fractional bandwidth is high, then it's a good imaging probe. If the quality factor is low, then it is a good imaging probe. Okay, these things are reciprocals, the bandwidth and the quality factor. So let's just summarize our transducers here. A pulse, we always want to have a short duration for good axial resolution. This would be an imaging transducer. For imaging, we want backing material to help create that short pulse. It has reduced sensitivity because of the fact that it has the backing material which sucks out some of the sound from the crystal, so it can't produce as strong of a electrical signal because of that. It has a wide bandwidth. It's a broadband probe. This is for imaging. Has a low Q factor for imaging, and it has good axial resolution. Non-imaging transducers have continuous wave or very long duration probes, and just so you know, non-imaging transducers are used specifically for vascular ultrasound in doing particular types of Doppler measurements of blood flow. So we don't necessarily are getting an image of the blood flow, but we see we have very sensitive transducers which can detect the blood flow. So anyhow, these do not make a picture. They're non-imaging. They are generally continuous wave or long duration pulses. There is no backing material on a continuous wave transducer. They have very good sensitivity, extremely good sensitivity, so they can use very, very little power to create their information. They have a very narrow bandwidth. In fact, continuous wave has the narrowest bandwidth you're going to find. It has a high Q factor, very high Q factor, and absolutely cannot be used to make an image with these non-imaging transducers. So let's talk about piezoelectric materials. So the Curie brothers discovered the piezoelectric effect back around the time when Marie Curie was doing her research into radium and radioactivity. Her husband was doing research into piezoelectric materials. And so Mr. Curie, I don't remember his name, let's call him, well, him and his brother were the ones who discovered this piezoelectric effect, and they were working with quartz when they discovered it. So piezoelectric materials, as we said earlier, either create electricity when they're deformed, or electricity is applied to them, causing them to deform on their own. There's a term called polarization, and this term is applied to piezoelectric materials when they are making the material, the crystals. They can do something called polarize them, and what polarization does is it takes a piezoelectric material which has its molecules in a bit of a random order, and we call this random domains, and when we make the crystal under polarization, it lines up those domains in all the same direction. Okay, so this is a good thing for our transducers. We want our transducers to be made by using polarization, because then the piezoelectric materials are enhanced due to this polarization process. Summary: polarization makes PZT materials more gooder. If you take a chunk of PZT material and you heat it up to a particular temperature called the Curie temperature, it will lose all of its piezoelectric properties. So you take a nice chunk of crystal, heat it up to a certain temperature, and all of a sudden it has no piezoelectric properties. So that is one reason, not the best reason, but one reason why we don't put our probes in autoclaves, is we don't want them to accidentally get overheated and lose their ability to detect sound. So we avoid autoclaves, and we avoid sterilizing our probes because that would ruin them. So what exactly is sterilization? Sterilization is the destruction of all microbes by exposure to extreme heat, chemical agents, or radiation. Okay. Disinfection, on the other hand, is the application of chemical agents to reduce or eliminate organisms. Disinfection will significantly reduce the microbial load on an item, whereas sterilization will remove the microbial load, including the bacterial spores. Spores cannot be sterilized or they will break. Okay, if you try to sterilize a probe, you will destroy it. Generally what happens if a probe is put in an autoclave is the epoxies that hold it together will break down and it'll just fall apart. So we don't do that. It could be that it reaches the Curie temperature, but the Curie temperature is usually around 600 degrees Celsius, and no autoclave goes up that high. Autoclaves are limited to about 180 degrees Fahrenheit, which is less than 100 degrees Celsius. Probes should be disinfected, not sterilized. Okay, just want to make that very clear. So let's talk about the transducer frequencies. In a continuous wave transducer, the frequency of the transducer is determined by the electrical signal that is sent to the transducer by something called the power transmitter or the pulsar. So the pulsar power transmitter will send an electrical signal to the transducer, at a specific frequency. The transducer then creates an acoustic frequency equal to that electrical frequency it received. That is a continuous wave or a non-imaging transducer. For imaging transducers or pulse wave transducers, a very short single electrical spike is sent to the PZT crystal, which causes it to vibrate. The vibration will occur at a specific frequency based on the PZT material itself. And that frequency is due to the speed of sound in that material, the stiffness of the material, and the thickness of the material. So that's why we had that 1/2 crystal thickness for the thickness of the PZT material was 1/2 of the wavelength in the transducer. So if we get a PZT material with faster speed, stiffer, we get a higher frequency. Remember, that's also going to give us more impedance differences. If we get a PZT material with a slower speed, we're going to get a lower frequency. If we have a thinner PZT crystal, we're going to get a higher frequency, and then a thicker PZT crystal is going to give us a lower frequency. For pulse wave ultrasound, this is an equation we can utilize to determine the frequency of the transducer. It is the speed of sound in a PZT material divided by twice the thickness of the material. That gives us a frequency. So one way to think of the PZT material and the sound that it produces, the frequency, is if you have a thicker crystal, you can have a longer wavelength. So this wavelength is much longer in the top crystal than in the bottom crystal. The bottom crystal is a narrower crystal, so it has a shorter wavelength. Well, the top one has a lower frequency because the wavelength is inversely proportional to frequency, and the bottom one has a higher frequency. So that would be, and you can take that analogy and see that if we put two of those smaller crystals together, we'd be able to fit two wavelengths in the size of the longer wavelength on top. Therefore, the bottom one is certainly a higher frequency than the top. Okay, this concludes the lecture on transducers, and as I said, I will be providing a separate lecture on bandwidth to talk more about that